We are live. We're live, ready to roll. How you doing, everybody? Welcome to at least this angle of the stream filming setup, whatever you want to call it. Today we're going to be discussing this. Now, if you don't know, this is out of a turbo core, and we're going to talk about some of the troubleshooting steps for this, and then how that compares to something like this. And this is all just kind of pre-leading up to diving into some of the questions. I do see we have a oil migration question. I do have another question I need to get to prior to that one, but we're going to get to everything today. So feel free to get your questions in and get rolling. Again, I'm just going to kind of kick off with this as a fun Kickstarter here. This is my desk setup, all right? So these are all my just various trinkets I've collected over the years. Decided to make a thing of it. I've wanted this type of setup for quite some time. Finally in a spot where it makes sense to actually put it together. I do have another setup that's actually going to be where I teach from. It's over on the other side of the room. That's a lot of the pictures I've been sharing is kind of that setup over there where the workstations and stuff are. Probably going to do some stuff over there at some point. I don't know. We'll see. I do apologize for any sniffling today. I am having some routine seasonal allergy stuff that I deal with, but we'll get through it. Good to see you, Jason. Good to see everybody in the chat. Hope you had a good week, and happy Memorial Day. Happy Memorial Day. Thank you for everybody who has served. It really does mean a lot. Your impact has far more reach than you may know. So I do want to say something that I think is really important and has helped me, especially for those who struggle with any kind of PTSD. It's okay to not be okay. You're not alone. You are supported. There are others of us out here who are doing this with you. So to thank you to all the veterans and everybody for Memorial Day today. And things are going to be better. I appreciate it, guys. All right, we do have the Lisa in the chat. Yeah, good. About to go buy office plants. Yeah, wow. Hey, you know what? I do want to say this is something I've been thinking about. She doesn't know I'm going to do this. She also doesn't like me talking about these things, but I'm gonna hit her with it anyway. I do want to give a big shout out, thank you to Lisa, which is my wife. So Natural INS there in the chat feed. She helps with the operations manager side of things and such, and the it really does. She cares so much for what we're doing and how we're doing it and what we get into that like she's severely sacrificed herself and her body to make this possible, right? So she deals with some stuff, all right, health wise, and she's put so much work and effort into trying to bring this place to life so that we have somewhere that we can train and teach and work from that she had a crash over the weekend, pretty hard crash. So we've had to spend the last few days getting her back up to speed and just getting her body recovered. She's doing better now. My point is she deserves to be recognized by all of us for what she has put in for getting this facility online, getting everything we have here put together so that we can be successful here. And I just really appreciate her and her sacrifice and everything she has done to just make all this possible. Right now, where are the kids? She's got them, right? That's what makes the stream possible. She just does a tremendous amount to make sure that all of this happens. So just a huge thank you from everybody, please, for Miss Lisa. And it means a lot. And yes, Memorial Days for those who have passed. I apologize for how I approached that. It's in remembrance to all of those who have passed. I also find it important to recognize those who didn't, and the guilt that you may carry by not being with the others. So I mean that in an all-encompassing way. If anybody just wasn't clear, I'm not always the greatest at explaining myself. That being said, how about we have some fun? We want to dive into some fun? Okay. So let's get this over here set up. So this is a IGBT module. Now, this is referred to by Dan Foss in the turbo core compressor as an inverter. And that's completely accurate, because part of what we have happening here is we have DC power coming in here. It goes through a set of transistors we call an IGBT, and we have AC coming out the other side. In that process, we're taking DC and we're converting it back into an AC, hence an inverter, versus a rectifier with like an SCR right here is rectifying from AC back into into DC, yada yada yada. Anyway, I want you to notice though there's two poles here. Okay, so we have a positive bus, negative bus as part of our drive assembly. Okay, there's a lot that there's a lot that should be familiar with this, and this is why I talk about very heavily that drive assemblies as a whole, they're all using the same basic principles. We have a DC bus. We have a two input. So like this is out of what you would commonly see out of a York, Danfoss York. Okay, these are the exact same thing. Even to the fact of this is one module unit. This is one module unit, but there's three individual sets of gates in here. 1, 2, 3, as you can see by the outputs. So we have a, technically these are the other way around. These are negative, positive, negative, positive, negative, positive, where this is positive, negative. That is not really all that relevant. The point is we have a 2-point input from the DC bus. We're coming off of a DC bus with a capacitor bank and all the things that we would have on either of these drive assemblies. And we're going to notice that these two modules troubleshoot very much the same. So it's very simple of what we're trying to accomplish with this. We're just trying to take a DC, we're trying to control the speed of a motor, the RPM specifically, and by controlling RPM, we're able to control how much capacity it's actually flowing through it, right? It's another form of trying to be more efficient and control capacity on some level. It's the same kind of concept that we would have on like a blower motor, okay? Let's take an air handler, a large RTU with a duct system that we're trying to control static pressure. We speed up or slow down the supply fan to control how much air we move through it so we can maintain a set static pressure, right? Well, in a very similar way, in terms of concept, literally very different fluids, we're talking air stream versus refrigerant stream, but we're controlling a compressor motor in order to control how much volume we move through the compressor, which affects how much cooling we're going to apply, ultimately in the end. So it's in terms of just why we do this process, it's the very core fundamentals of just where these theories on how we're going to control this come from. Now, we'll grab a meter. So I'm going to set this to diode. Okay, so this particular meter, the diode and continuity share the same setting, but I'm specifically focused on the diode. So what I expect to display here is a volts DC. All right, so I'm going to start with putting my positive lead on the output of the module, and I'm going to go negative lead to the positive bus side. That's a 0.311. That's volts DC. I'm going to go to the negative side. I get an OL. Cool. We'll get into the numbers here in a second. I just want to show you some of these things. All right. Now, I'm going to flip my leads. Negative lead goes on the output, on my inputs. So earlier I had 0.31. Now I have OL. I go to the negative input. I have 0.31. Let's switch to the next leg. We have 0.31 and nothing. Okay, so I went negative to positive that time, so I didn't follow the exact same sequence. Hopefully you're able to track. So I'm going to go positive lead to the output, negative to the positive input. We'll round that to 0.31. It's close enough. And OL. Excellent. So these two measured relatively identically. Cool. Now, this is my input side, this is my output side of this module. The way that I always track with these is my 16-pin bus or Molex plug always goes on the, from this angle, technically I'm looking from the back of the drive forward. Technically, we would be servicing it from this way. So if I was sitting in front of the panel, this would be on my right-hand side, and with this on the right-hand side, I know that this is my output. If this is flipped around and this is on the left hand, then that indicates to me that, you know, this is still my output side. Okay, so, and that's what I picked up on in terms of being able to tell the orientation of the module. Okay, so that being said, these two, I'm actually going to flip over to ohms real quick, and I want to show you. Reading across here, we should get 0 ohms. I was really close to it. See if what this one says. All right, so it's not quite perfectly 0. What about this other side? Yeah, see this other side we get OL. So this would be another way to indicate to yourself if you're not sure with a setup like this, because they do look kind of the same on either side. This side has continuity because this is the same output. We would have either a bus bar here, and that would be one phase of power output coming out. Okay, switching back over to diode. So it doesn't matter which of these I choose, I'm just going to pick one. And I can show you that is true here in a second. So I'm going to go positive lead on the output. I'm going to go to the positive terminal. So we have 0.36, we'll round that up. I'm going to go to the negative terminal, and we get OL. Cool. Flip them around, well actually, just to show my point, and I'm going to go to the other side. Yep, 0.36, exact same reading. Exact same reading, okay? Just to show that there's not a difference on this output side. I'm going to flip the leads around. Negative to my output, positive to my positive input. OL, cool. We had a reading once before, it was 0.36. And then this had OL before, but we have 0.36-ish, close enough. That's awesome. Let's try this other one. I'm going to do it reverse order. So we get a reading, 0.36-ish. OL, flip it around. OL, and 0.36. Do you understand my point here that I'm trying to show you on? They look radically different. They look radically different. But in the end, we're using the same technology. We're using the same transistors inside of here through an IGBT assembly, and there's a whole lot more we could get into with like what the actual electrical circuit looks like in here and all the things, right? There's so much more we can talk about, but I just want you to, if you learn how to troubleshoot one or the other, you're good. Now, the readings on these are technically considered within spec. So like for this, we would use the Turbo Tool app, and I can show you that here in real quick. Nope, that's the wrong one. All right, so here's Turbo Tool. Okay, so we can go to verify. We want to do a top side verify, and I want to verify inverter. All right, so here's my inverter values, and they want to see if you can zoom in on that. All right, so they want to see 0.275 to 0.4 when we get a reading, and they want to see OL on the other side. And you're going to do this per leg of this. So just to kind of show you, now these are very generous numbers. Okay, I can say from like my background and my experience, usually I want to see between 0.36 to 0.38 is what a lot of these will measure at. Now, most of the manufacturers will say that technically, as long as you're within 0.3 to 0.4 VDC, you're considered good. Now, the particular one that Danfoss is using is actually, they're saying, hey, as long as you're within 0.275, which I think is quite generous. For me, by the time I'm getting that close to the edges, I start to get fairly nervous, right? So this one being 0.31, it's considered good. If we're not having any symptoms, awesome. But I wouldn't be shocked if I was having symptoms, at least occasionally. Which, keep in mind, an inverter on a turbo core with a mag bearing, inverter issues can represent as bearing faults, because part of what will happen when these inverters begin to fail, they don't control the magnetic field properly, and that causes instability in the rotor. Well, the sensors on a mag bearing are going to sense that instability as a bearing issue, because, well, it's because the bearings are having trouble controlling that now. And it's not because the bearings themselves are going bad or having an issue. It's actually, it could be the inverter is beginning to show early signs of failure, which the closer we get to that 0.275, for example, or 4, either of the extremes, the closer we get to either of those, the more likely it is that we're going to start to see more of those instabilities, because typically, in my experience, these will be closer to that middle point if they're in extremely healthy condition. Now, this is all just very rule of thumb, generic stuff, right? So what I'm explaining is not just like a hard set rule. But just because these test good, I guess part of the point I want to get to here as well is, just because these test good does not mean that they are good. Because part of what can happen is they still test and they still function, but they're going to start having symptoms like I'm describing. And the point of this test may be that, hey, let's say we're tripping faults, we're blowing fuses, things of that nature. These are some of the tests we should do in order to verify, hey, is this even safe to turn on, right? So if we are having an overcurrent fault, especially as soon as it goes to turn on or something, before we try to go any further, or if we have fuses blown, period, before we go any further trying to put new fuses in or reset things, we want to get in here and make sure that these types of modules, this is true for the IGBTs or the inverters, true for the rectifiers or the SCRs. Like, we will have to verify this whole circuit before we try to put power back to it, because these components will literally explode on you. Like, if you're not careful, most of the time they're not going to literally explode. They're going to crack, or they're going to fracture, or something crazy like that's going to happen. But there are scenarios where these will just internally short to such a degree that they go boom, literally boom, and grenade from there. So have to be very, very careful when we're working on this stuff, and making sure that the DC bus, like all power is completely dead when we get in here to do this kind of work. Ultimately, both of these follow a very similar track. I know York does state zero point 0.3 to 0.4 is their tolerance on their IGBT modules like this. We just talked about Danfoss, and it doesn't matter whether you get into Daikin or Train or pick a brand. When they have a drive module like this, all of them that I've worked on, that to my memory, all followed a very similar kind of thought and track. So once you learn how to troubleshoot one of these, you really have learned just troubleshooting the process, the whole troubleshooting process. Think of it like a thermistor, okay? Do you truly care that much about the brand of thermistor that you walk up to? Or do you just understand that, okay, this thermistor has a resistance? Now you need to understand the range at which that resistance can vary, right? So is it a 10K, 20K, you know, what is is it type 1, 2, 3? Like what's its range value? So that's important, yes. But ultimately, it's a thermistor. Or similarly, what about a transducer? Okay, yes, to fully like dead on verify via the transducer's output what its pressure should be at that voltage output or the reference signal coming back out of it. We need the chart for that transducer, or you know, we can use other comparative gauges to compare, okay, transducer to this transducer. But like my point is, we don't walk up and we try to verify, okay, what brand is this transducer and how am I going to troubleshoot that transducer, or what brand is this contactor or this capacitor, and that's going to radically change how I'm going to troubleshoot this contactor or this capacitor. No. These modules are very, like, it's when we get to the same technology the way that we are, like this technology is just the technology, it's just how this works. And you can take that approach with this and don't walk up thinking you have to relearn or learn exactly how this specific one functions as if it's different than this one, because it's not. Now, just for fun, because this is something that a lot of guys do in my hands-on class, right? So I do have my hands-on class schedule posted for this year for the fall season. So I have an August, October, November, and December class you can get signed up for. Here in Fredericksburg at this facility, August and December are those two classes. But guys always love to kind of take this apart. Now, this is not something you would typically do in the field, but for fun, what does it look like under here? Let's just take a look. Those are out. Yeah, this one's one of the ones that's been taken apart at least a couple of times. Okay. All right. So this is your gate driver board. So is this green top right here. These are your gate drivers. Your actual gates are these white modules underneath, which is what these are. Okay, these are the actual white modules, or the transistor modules themselves underneath. Now these turbo core use these little push pin deals that are what's making contact between the driver board and the internal gates of the transistor. And we could even strip this apart further. We can see one of those. We'll just do one of them. Again, if you haven't, this is one of the reasons why I encourage going to trainings where they allow you to do this kind of stuff, because like this is not something you would do in the field. You're not going to strip this down in the field and do this. If this module was to fail, you would just replace this whole plate assembly, because this is the cooling plate that it's sitting on. The DC converter would go here. Your SCR plate assembly would attach over here and kind of come up and out. Anyway, but when the thing doesn't have to go back together and actually turn on when you're done with it, you get to have fun and kind of see just what more else is under there. Let me get this clip. Okay. I'm not going to tip it over. All that is underneath there is a insulating pad. And if I tip it over, all those little pins are going to go flying everywhere. And I don't really care to do that right now. But you can see this is your actual IGBT transistor here. And we have our positive coming in. There is still insulation here between the positive and the negative. That's what this lamination paper is. And then we come out of our IGBT module and into our actual output here, the output bus terminal. And then these are those little pinpoints that we're going down and making contact with the IGBT assembly, or the gates themselves. So the gate, you could think of a gate like you would think of a coil for a contactor. Okay, so we're going to energize a gate in order to activate the transistor. Okay. I'll worry about putting all this back together later. Just to kind of show you something, if you haven't got to see something like this before, just some fun. This is what it looks like on the inside. And in terms of like this pin out here, same thing here, that all this ties back to our logic or control board assembly, which communicates to the gate driver. The gate driver then activates the gates of the IGBT modules. Again, this is a three module bank or assembly where we've got three different sets of IGBT modules built into one master assembly. So this is telling those how to fire and trigger in order to run. These could be ran in three-phase where they're 120 degrees out from each other, or they could be ran as a single phase of a larger three-phase assembly. So this may be one leg of power, and you'll have a solid bus bar coming across here. And what that does is it distributes, say, A phase, or B, let's call it B's. So it distributes B phases current across three modules instead of having to have one really large module to run just that one leg of power. So now we can have that distributed across the three, and then the three can then carry that one phase, and then you'll have two other assemblies. So you'd have A, B, and C phase all coming out of each module. Anyway, fun stuff. Fun stuff. Make it situated here. Okay. Catch up on the chats here. From Miami, Florida. Good to have you, bud. See, 5 volt in, 2.5 volt out is half of the range transducer output in a nutshell. Yeah. Well, I mean, and that's if now most transducers, to your point, Tom. How you doing, Tom? By the way, most transducers are fairly linear in their meaning that they have a fairly straight line on a graph, but not all do. Some of them are non-linear, and so you'll have this kind of sliding scale range of how much the pressure fluctuation affects the VDC output. Now, again, the vast majority of them are fairly linear, like close enough to linear that you could call it a linear scale. Which at that point, you know, if you've got again, if you do the math on it, if you know you've got 100 to 200 PSI range on this transducer, it's called, let's say it is a 5 volt VDC transducer, then your output at 2.5 volts, you would expect to be 150 PSI, and then you could run the math from there to adjust your scaling accordingly. So theoretically, it's close enough that you'd probably be correct, but it's not a hard number. Those are some rules of thumbs we can go by if we need to. If we're just trying to get something, just need something to get a handle on what we're doing. Mostly lower voltage or MOSFETs. You can change the gate. We read continuity both ways. Yeah. Okay, let's get into our first question for today. I'd like to see a video of how, as a contractor, you would set up both a pack heater service loadout for getting vacuum chillers to a positive pressure for service, as well as how you would build your kits for recovery of vacuum machines. Getting ideas for kit building. All right. On this, I personally recommend the RefTech line of equipment. Like, especially for dealing with low pressures, by far, absolutely awesome. Can you build custom rigs? Absolutely. There's plenty of people out there. If you ever work with a Rapid Recovery, for example, their machines that they run around with are some custom designs that they did in-house. But from a general contractor's perspective, I'm a huge fan of what RefTech has done, their machines and equipment. They not only have recovery equipment, but they also have the pressurizer. So let's talk about the pressurizer first. So to show you, this is the one that I personally prefer and like to use. So you've got the actual pressurizer unit here. It's just going to connect. Now, they actually recommend connecting this on the evaporator. Typically, when I've done this, I've always gone through the condenser, but the point of being able to do it in the evaporator instead is you're actually putting that heat to the liquid refrigerant, because on a machine like this with the low pressure, you're dealing with a flooded or hybrid falling film barrel, and ultimately all of your refrigerant at idle is going to be stacked, your liquid refrigerant specifically, is going to be stacked in the evaporator. So the whole point of that is by doing it on the evaporator side, we're getting that actual liquid refrigerant heated up. Now, the points that cause me caution for this is I don't like, it bothers me messing with the chemical treatment or potentially messing with it by connecting to the evaporator side, because these are almost always going to be a closed loop. Whereas on the condenser side, at least we're dealing with more of an open loop, and we've got a chemical station that's constantly monitoring and replenishing and like maintaining the water treatment on the condenser side. Whereas on the evaporator, on a lot of plants, especially smaller plants, you're not going to have that same chem feed on the evaporator side. Now you absolutely will in some scenarios, but in many of them, especially if you're dealing with a comfort cooling, it's not a process system with glycol, you're not going to have any kind of treatment. It's something where it's only when the chemical guy comes out and actually checks the treatment levels on the evaporator or on the chilled water side that you're going to see that. So that's why for me, I'm cautious to do that approach, but it is a faster, better approach if capable or if you're comfortable doing that. So this machine, it has it can wire in multiple voltages in various ways. You can tie it into the actual chiller's control or input panel, whatever the case may be. The whole point of this is to pressurize the machine up above a negative pressure specifically. So with a low pressure machine, like part of the whole definition there is these machines operate below atmospheric pressure, especially on the evaporator. And when these machines are in an off state, they will typically sit in a vacuum, even if it's negative 1, 2, 3 psi below atmospheric. And that's gauge that I'm speaking in. Which in absolute, it would be at, say, 12 to 13 psi gauge, or not gauge, absolute. That means you're sitting below atmospheric and you're in a vacuum, right? And anytime you service this, like change out the purge filters, change your oil filter, do anything of that nature, or if you're trying to take an oil sample from the bottom of the oil sump, all of those things are going to cause you issues and have potential of drawing in atmosphere into the machine. So we want to get this pressurized in order to get above um, that neutral, or that less lower than that vacuum. We want to get above the vacuum. That's what I'm trying to say. Damn it. This quite literally does that just by recirculating hot water. Now you're isolating both of your barrels, and when you're doing this, you don't want to have, at least I personally, I want to have both barrels completely isolated. I don't want the heat I'm putting into the machine to be able to trickle out into the rest of the water loop. And if your ISO valves on the barrels are not holding very well, especially the chilled water barrel, this whole process is just not going to work. You're not going to be able to get enough heat flowing through there to get the machine's pressure up, because like, even if it's just a bleed by on the valve, it's going to keep enough cooling going through there to get you. And I do mean fully isolate on both inlet and outlet on both barrels, not just having an ISO for flow to stop flow. I want to actually completely isolate this from the rest of the circuit. So this has a pressure transducer that can connect. You can set a pressure setting. So if I'm just doing a regular routine service, once I get to 1 psi, I'm happy. I can change my purge filter, I can change my oil filter, I can do all the regular service. When I get to the point of trying to leak search, I like to go somewhere between 5 to 8 psig specifically on my leak searches. Again, if you prefer to work in psia for atmospheric, then you're more than welcome to like convert that accordingly, and that's going to depend on your altitude and all that stuff. So that's just my personal preference. If I'm leak searching, that's what I'm going to do. If I'm just doing regular maintenance and I don't plan to do a leak search, then I won't worry about trying to pressurize it as high. And how long this process takes depends on, what voltage do you have available? Are you running 230 through it or 460? Do you have a larger machine? How large a machine is it? Do your isolations hold properly? So there's lots of variables that come into play on how long this takes. Now there's ways to build these, absolutely. Let's see, I think I saw one. Yeah, I mean, quite literally, I have done this by running a trickle from a mop sink and a hot water heater, right? I don't necessarily recommend that. That's not a best practice. Best practice is to have an actual heating unit. If you could build something like this, if you had you quite literally just take a barrel, find a way to mount and isolate, because you got to think all this is going to be pressurized, okay? So to bear that in mind, this is a pressurized loop on either side. Well, your condenser may not be pressurized in some cases, but you're dealing with a pressurized water system. So it can't be just an open vat, like an open barrel. But if you can get a heater in it and you can hook up a little transfer pump, and you're willing to manually monitor the pressure to make sure you don't overpressurize and such, like, by all means, there's ways to build these yourself, or you can just go get RefTech's set up. And just to show you, some additional on how this is going to look inside. So you've got your machine. We're pulling off the evaporator. We're going to pull into our pump. We're going to push that through into the heat chamber. It's going to heat that water up, send it back out, and it's just going to constantly recirculate on that heat exchanger until we eventually hit our pressure set point. Now, what's also really cool about these RefTechs is the pressure sensor will it'll keep everything online to where once you hit your set point, your pressure set point, if it sees that it starts to drop below that set point, let's say you were leak searching, you've got a large machine, you wanted to keep it at 5 psig. Well, at that point, you can just it'll turn itself back on and keep and recirculate again in order to maintain the pressure once it sees the pressure begin to fall, which as the machine just cools due to, let's say, just ambient alone, it will begin to lose that pressure. So this will help you kind of self-regulate that without you having to manually monitor it, do it yourself, things of that nature. Really, really great setup. Now, in terms of their recovery, they've got a few different lines. They've got the low vac, the cheetah, they've got the all vac. I personally, like, if you can get it, just go for the all vac. It is the one, it's just the granddaddy of them all. Okay, it does all the above. You can do high pressure, low pressure, your POE and mineral. Now you got to change the compressor oil and stuff, but you'll get into those details as you're learning to use these larger systems. And you're talking about using 1/2 inch and 3/4 inch hoses at this point for this transfer. That would be recommended. I think their smaller systems can use like 3/8 or 1/2 inch. But if you're going to hook up something like that all vac, you're going to want at minimum 1/2 inch, if not preferably 3/4 inch hoses going through that. So that's going to be part of that setup. And the all vac, like by far, if I just had one machine to do this kind of work with, now I'm not going to take this all vac out and go use it on an air cooled machine or some smaller, some small, say, high pressure machine like a WMC. You absolutely could, but we're talking such small volumes and such. It's easier just to carry that Navic NRDC 4M, which is my personal preference. I've got mine right here, right? Right there's the NRDC 4M. Absolutely wonderful machine. By far, I will advocate for that until somebody figures out a way to beat what Navic made. I know that there are others like it. I think Philpiece has come out with their own competitive version, but it is not the same. It does not have the same subcooler circuit. It doesn't compete on the same level, in my experience, that this Navic will. This Navic is truly an absolute monster. And like from a recovery kit, so if I'm doing a small centrifugal like a WMC, we're just moving a few 100 pounds at a time, or if we're dealing with an air-cooled system, whatever the case, that's what I'm grabbing. And then when we get into these larger systems, larger centrifugals or low-pressure machines, stuff like that, that's when I want to have that all vac on hand. Again, that's not the only version they make. They make other versions, and you can talk to the guys over at RefTech about which one works for you. I am hoping it'd be really cool if for our training facility here, we can get an agreement set up with RefTech. I've been talking to their guys for quite some time now. It'd be really cool if we could get some of their equipment in here as part of our hands-on training and stuff, where we can actually go through the process of hooking up and running the large machine like that in a test environment for just practice and training purposes. So from a low pressure machine, which when you say vacuum machine, that's a more technical way of saying that is it's a low pressure. With that setup, I'm going for those two RefTech setups. The pressurizer, which you don't need the pressurizer to do the recovery. The pressurizer is there if you're going to just be doing service on the machine. Your regular maintenance, leak search, things of that nature. Maybe you want to swap a well, that's less true, I guess. Either way, if you're just doing, think of it from a maintenance perspective, whatever the case may be, that RefTech heater will get you covered. Then you can get whatever line of recovery machines that works for you, transfer machine. Like I said, just if you want to just do a one and done, let's get the machine for the rest of our career. And like RefTech sells parts, they will support you on these machines. Like you can repair them and such, which is part of like why I prefer them so much. They're serviceable. They're not just a buy it and figure it out or stuff like that. Like RefTech has a pretty good support line. That being said, that all vac will get you. If you want to go with a smaller line, something like that, that's fine too. And yeah, so the liquid pump is one that comes up as a frequent point. For me personally, once you get a proper, like if you can use a liquid pump, then vast majority of the time you're capable of doing either a push pull, and if you can't do a push pull, then you at minimum have access to being able to do a pull pull. And it is my personal opinion that those will outperform what a liquid pump will do without having to carry the extra liquid pump around. Now, RefTech does also make a liquid pump for refrigerants, but liquid, like it's just at some point we just get into personal preference. Ultimately, mine is I just as soon hook up a push pull setup and roll with it and not worry about a liquid pump. And that's true whether I'm charging refrigerant or recovering the refrigerant. Others have a different experience with that and are happy to go with liquid pump. And again, that's just what works for you. Okay. I'm just sharing my opinion, what I think, my position. You make the best call for your situation. Yeah, Welch pumps are really good. They are good. Now, I do like the Navic. Kind of see the top of it. This is the NRDC. Is that right? What did it say? Yeah, NRD 24M. These aren't technically just open on the market. You can get the NRD 16T from True Tech Tools. By the way, offer code HVAC time. Get you some discount on there. You can get the 16T, and these are absolutely incredible. I love these. They manage thermal performance extremely well. They've got a really large reservoir, which is very similar to the Welch. That's one of the benefits of a Welch, is they have such a large reservoir on them for the vacuum pump oil. So you can, if you do have a wet system, you can get more life out of one run without having to do an oil change so often. That's one of the detriments of going with a small machine or a regular vacuum pump we would use on just kind of everyday stuff, is they don't have as much of an oil volume. So things like the Welch pumps or these industrial pumps from Navic, they have a much larger oil volume, and the benefit to that is you get more run time with a wet system before you're having to cycle that around. And that's regardless of whether you've got a cold trap involved or anything like that. But one of my complaints with the Welch is they're not as portable, okay? They're not as portable as something like what this Navic is. That again, in terms of this, why do I prefer this over a Welch? I've had better experience with getting this to move around. They got little dolly carts for it and stuff like that. It's just more portable, and it does an equivalent job in my experience, in my opinion. Yeah, that's what it boils down to. And being 18 CFM versus say like 12 or 16 or 18, like by the time we get into these ranges, the CFM matters a lot less to me as much as the actual hoses and the configuration of what I can hook up to. I'm not too, once I break over 12, I really don't care that much how much CFM that pump can do, because getting my hoses to perform at even just 12, much less above that, is part of the main challenge. Then is, okay, now I've got to get my hose assembly set up in a point where I can even handle that much CFM. And there's going to be that much CFM at the upper end of the pull down. As we get down into the deeper parts of the pull down, like we're just not moving that same volume of CFM anymore. So like just the bigger CFM pump isn't necessarily just always better. Okay, let's move into, yeah, I've heard a lot of good things about some of the JBs here recently. Heard a lot of good things. I knew JB from a long time ago, and I don't know, just they were a pump. They weren't anything impressive. But I think they've seemed like they've improved their game as of late. All right, let's get to this question, y'all. Give me 1 second. Okay. I'm going to shrink this a little bit because it's a little big. Still getting everything dialed in for my new setup. Okay. My oil charging oil sump 1 week after oil level low alarm, no leak, so no leak at all in the system, and condenser saturation and oil sump temperatures all almost above 3 degrees. Only what cause any oil migration? Okay, so we're having low oil alarms. We don't have any oil leaks. If we did, there'd be a ton of oil on the ground. We don't know what machine we're working on, but just from a general standpoint, like it gives us something to start with. If you want to tell us like what model that we're working on here, that could be helpful. It may not make much of a difference. There are some models that have a little bit more of a um, variance in how they perform. So, okay, so it ran for a week. We have a low oil level alarm. So we're thinking migration since we don't have a big oil slick underneath the machine. No leak in condenser system, condenser saturation, and oil. So we're keeping condenser sat and oil sump temp up if I'm tracking. I would question, I just want to make sure the oil heater is actually functioning. How do I approach this question? The oil charge. How about we just take a migration approach in general? What are different ways we could have a migration event? So one would be if we in the off cycle. So we could have an off cycle migration with we could just have an off cycle migration. This could even be true, excuse me, depending on the machine, even if you have oil heaters functioning. One that's really bad about this is an RTHD, sadly, by Train. So they're notorious for in the off cycle. They just, especially if you don't have your evaporator isolated in off cycle, like if that machine is off, that evaporator cannot have flow through it at all. And I've had that happen with machines where they get just a little tiny trickle, which for a lot of machines isn't that big a deal, but for these RTHDs, they really struggle with it, where the ISO valve for flow doesn't 100% stop, and it's just this teeny little trickle, but it's just enough to keep the evaporator cold in the off cycle, and it just sucks that oil right out of the sump. It's a pain. I've also seen it to where during the off season, if your plant gets really cold, it'll get the evaporator to stay cold and it'll draw that off. Anyway, so you could have an off-cycle migration. Now, most of the time with an off-cycle migration, I would say it's more common that the oil heater itself is not functioning correctly, or we somehow got a ton of refrigerant into the oil sump, which that could be an adductor issue where the adductor is getting overfed on the adductor is getting overfed on the refrigerant. So there's a balance. Anyway, we have to calibrate a lot of the adductors we have in the field. So if that adductor is not set properly on the valves, you can overfeed your oil return line coming through the adductor, and that's going to introduce a lot of refrigerant into our oil sump. So if that oil sump is heavily entrained in refrigerant, even though the heater is functioning and we're technically at temperature, when that machine goes to shut down, if that heater for some reason didn't work correctly, or we just had too much oil or too much refrigerant entrained in the oil, we could end up causing what would be considered an off-cycle migration, where that refrigerant ends up carrying that oil to the coldest point in the system, which is likely going to, or should be, our evaporator. So all that oil is just going to get sucked straight to the evap and moved with that refrigerant as it goes. So an off-cycle migration due to an oil heater, something like that, would be one example. Having our an eductor issue. And I say eductor, how about this? Why don't we call this a oil recovery circuit? Because not all use eductors. Oil recovery. So if our oil recovery circuit's having an issue, and I apologize for the mic. Maybe turn this down a little bit. It's coming in kind of hot there. If our oil circuit itself is having a oil recovery issue, so this would be an example of, we've got a flooded or falling film evaporator specifically, then those are known, or those will need a oil recovery circuit in order to get that oil back. Now, the most common ways with an eductor, which you can call a jet pump, eductor, same thing. It's just two ways of saying the same thing. It's got multiple names for it, kind of like IGBT versus an inverter, yada, yada, yada. Anyway, we could also use what Trane calls a gas pump. They've also started using a gas pump style setup on their air-cooled lines. So on the newer Trane air-cooleds, they've got a gas pump type assembly with a little heat exchanger where it collects the oil in the bottom of it. We open a hot gas bypass valve or discharge gas valve, not bypass, but discharge gas valve, and it sends that oil back into the compressor that way. Anyway, so an RTHD, a ACR, RTAF, I think even the RTAEs, all of those are using a type of gas pump style oil recovery system. Anyway, if this isn't functioning correctly, then that can cause the migration problem. So ways it could malfunction. One, the eductor filter. So these will have some kind of filter dryer involved. That could be plugging up, not allowing enough flow through. And this is going to be leaving the eductor. So if we leave the eductor block or the gas pump, whatever the case may be, and head to our what we're feeding back into, whether it be the compressor, the oil sump, whatever the case, if that's not feeding correctly, or if it's the filter's not allowing enough flow through it, that can allow the oil to begin to stack up in the evaporator. So that's one example. Another would be if the refrigerant level starts to run too low or too high in the evaporator, which that could be undercharge, overcharge, liquid level sensor issues, metering valve issues. Those would be reasons we may have improper liquid levels in the evaporator. So if the evaporator level starts to run too low, then the eductor can't access the oil, which is sitting on top of the refrigerant. And if the liquid level begins to run too high, then all that's going to be coming back into the eductor is straight liquid refrigerant, because our oil gets pushed up above where the eductor is pulling off of. So that's part of what we're having to balance, but that's that's going to lead to a migration eventually. If we can't stay within what's our designed liquid level point on that heat exchanger, if we can't stay there, then our eductor system cannot access that oil and get it back out of the evaporator into the oil sump. So eventually, you let that run long enough, that's going to cause a migration issue. If the eductor valve coming off the evaporator is not calibrated correctly, so with a lot of machines, we have to manually set that valve. It's not just to leave it wide open. But if it's closed off too much and you don't have it open far enough, then that can cause the liquid or the oil to stack because it's just not pulling enough volume off and sending that back to the sump. So it could be a calibration issue for your eductor return line coming back into your reservoir, your oil reservoir. Let's see, how many other scenarios? We talked about low, high level filter, the valve calibration. If we get too low of a DP across the machine, so but by DP I mean differential pressure between the evaporator and condenser. So we need that differential in order to help facilitate that oil return and to get enough discharge gas pressure to come back through and hit that eductor block and pull it back out. So having enough separation, a high enough DP across there is important in order to get that oil back. Now, all of this is just assuming we're discussing a flooded or falling film evaporator. If we're talking about a DX style shell and tube or a braze plate, it's a much simpler process. There's less involved there. For those, it's just strictly about velocity. But for flooded or falling film, this is where we have all these extra variables and trying to manage getting that oil back out of the evaporator. So, yeah, we have to have enough differential between the circuits. That's one of the issues with running too cold of condenser water on a water-cooled system. You can get the DP too low if you're not careful, and that low DP will result in oil migration. Like that will be the failure. And that's if you don't push it into a choke condition, depending on your load, because you just don't have enough lift in order to maintain the mass flow. Let's see. Off cycle, oil recovery. Migration. Yeah, those would be the main things I'd be looking for, just kind of getting back to the original question of we don't have a leak. We just had to add oil to the sump. 1 week later, we're getting these alarms. Now we don't know the model of the machine. There's a lot of details we don't know. So everything I've discussed so far is very much just from a general perspective, just as a whole. This is things that I'm monitoring for and trying to make some assumptions without getting too specific to any one thing, just so that hopefully this answer can be easily applied to whatever it is you're dealing with and what your scenario is. If we're dealing with like I was saying, a braze plate or a DX shell and tube, it quite literally is just get your velocity up. All right, you can do that by just raising the condenser pressure set point. You can do that by shutting down a couple of condenser fans. Just force that head pressure up more, because usually that oil is migrating due to you've got an unloaded condition Usually we're going to have a low ambient condition. We've got lower head pressure, so our DP or compression ratio is lower on the circuit at that time. So typically for those machines, when you've got these conditions starting to line up and we've got low velocity, low refrigerant velocity moving through the heat exchanger, the evaporator, that's when we're going to start to see that oil begin to stack because it can't get carried back through the suction properly. So it is as simple as just get your velocity up, increase your DP, and you'll get that oil to return back. Now that can be tricky, so if you're trying to bring a machine on that migrated in the off cycle, which is very common, especially because these, like a lot of these circuits will share with another circuit. So that evaporator may be a 2-circuit or 3-circuit evaporator. So we've got multiple refrigerant circuits acting on it, and it may be the case that Circuit 2 hadn't ran for quite some time. Circuit 1's been online maintaining the load. Circuit 2 finally goes to come on, but all of the oil has already migrated because we didn't have proper, or this manufacturers did not have isolation on the oil circuit to prevent migration from happening when the other circuit is online. But that other circuit's creating a cold evaporator and making it easy for that oil to migrate. And it's not uncommon for some of these air-cooled machines to not have oil heaters on the oil separator or something like that. Many of them do. They may have a crankcase heater on the compressor, but the actual oil reservoir, which is typically an external, not always, some of them are integrated into the compressor, but many of them are external reservoirs via an oil separator. And they a lot of times will not have a heater on them, so having those migrate is very, very common. So it's just a matter of you have to try to get that circuit online and get the DP up fast enough in order to get that oil to return before we start having faults and issues. And it's very, very, very common in low ambient scenarios where you may have to cycle that circuit and let it trip on that oil fault a couple of times before it finally will come on, and then it's got enough oil to return from the couple of startups it's had. It's had just enough oil come back, and then it can stay online and keep the compressor safely running with the oil circuit. So just some stuff you may run into with that. See, was curious on oil temp versus yeah, simple check valve. So the having an ISO valve, you wouldn't want a check valve for migration because at that point, typically the circuit has equalized on these machines. Usually, some of them will pump down, but a lot of them don't. Or they don't pump down and stay pumped down. They'll do a pump down initially, but then with time the circuits will still equalize because it's not fully isolated. Either way, when we're migrating, see, a check valve works when we've got actual like forced flow one way or the other. But migration, there's no forced flow. It's quite literally just a natural movement through the circuit. Now you can have an isolation valve and you can have an automated isolation valve, like a solenoid valve. As an example, you can use that to isolate and try to prevent the oil circuit from being able to migrate. The thing is, like, having those added features makes a more complex control system, a more complex oil circuit, more things to fail, more expensive because now more beyond just being more complex. Now it's going to cost more to manufacture that machine that has that isolation valve built into it. So you get into this cost and complexity just fight, if you will, or battle between, sure, we could do that, but then we're going to have to sacrifice on these other things to do that. That's when I've ran into this conversation. It's like, yeah, there's lots of things we can do,
but there's also ways to kind of manage it and mitigate it and not have a problem with it, and they prefer to just do that. So it leaves it up to us as the field technician to manage the migration issues instead of having it fully isolated. I'll use like a RTAC or a YVAA as two examples of like why they have full circuit isolation. Like a YVAA has a suction isolation valve, and it's a butterfly that they put in the suction line. The whole point of that is actually to prevent a refrigerant migration freeze, which is a very different condition than oil migration. Okay, we're talking about two different things here, but the reason that became necessary and it became worth it for York to put that in, because they were having issues with migration freezes on their falling film evaps, and it was rupturing tubes in low ambient conditions. Not because the temps got too low outside, not because the evaporator heaters didn't function, but because the refrigerant migrating to cold condenser coils at shutdown due to just a rapid drop in the condenser temperatures due to low ambience has a hard enough natural draw on that liquid refrigerant, lowers the saturation, tubes bust. So because that was giving them a negative press and it was causing legitimate issues for the customer, then it became worth it for York to add those extra valves in place. It's the exact same conversation of, well, why don't they do this for oil migration? Well, realistically, it's just not become a big enough issue to justify adding it versus just making it something we deal with in the field. Hopefully that makes sense. Just kind of catching up on the comments here. Clogged oil filter, clogged oil returns. Yeah. Yeah, so that's right. Managing, that's one of the cool things about how that those Daikin, where those the turbo screw compressors function with their dual slide valve. So because it's basically what it is it's variable ratio, volume ratio is how Daikin refers to it, which is just volume indexing. Is how the rest of the industry refers to it, is VI control. So they're using VI control in order to it does more than just keep the point of volume control is to match the actual compressor internal volume ratio of from the output of the screws to the actual system ratio of like compression ratio between suction and discharge, which helps make the system more efficient, less wear and tear on the compressor. Something that does play a part in is by keeping that compression ratio proper, it will help with that oil return to a degree, but it's less focused on oil return. Like the whole point of that VI control is less to do with like oil return and more to do with matching internal ratio, volumetric ratio in the compressor to system ratio, and those two making sure we're matching so that we're not over compressing or under compressing the refrigerant inside of the compressor to the system. And so like just for some clarification there, like it's the condenser fans will have a bigger impact on those Daikins than that internal ratio would, because the internal ratio is more to do with wear and tear and efficiency of the system than it does oil return necessarily. I don't know if they may teach that different. If they do, Jason, I am curious. Feel free to kind of fill in some blanks there. But with my background on the topic, it's less to do with oil return and velocity of the oil. That has the system ratio has more to do with the velocity. The compressor internal ratio matching the system is more to do with wear and tear and efficiency. That's maybe a simpler way to try to say that. It does. I was odd on twin compressors sharing a common suction line with a seems like monoflow type uh, fitting internal. Don't know much about ever learning when possible. I was odd. Sorry, I'm just trying to catch up on the comments here. Was odd on twin compressors sharing a common suction. Oh, so you're saying that the suction line had a type of valve that only allowed flow to one compressor at a time? Yeah, I'm just curious as to a little more detail on what you're referring to. It sounds interesting. If you have a model number, that might help me kind of connect what you're referring to. A chiller technician, good at mechanical side, but I struggle with chiller controls. When I look inside the panel, the boards and wires confuse me. Yeah, fair enough. It's a lot. It's a lot going on in there. Do you have any advice to help me improve? Let me make sure we didn't have another question. I think we may have had one other question earlier. If not, we'll jump to that. Okay. Yep, let's do this. Give me 1 second. Okay. I'm chiller technician and good at the mechanical side, but I struggle with chiller controls. When I look inside the panel, the boards and wires confuse me. Do you have any advice to help me improve? This is something that we all absolutely struggle with. You are not alone on this process or this journey. Like, it's a lot. It's a lot. I tell you, the biggest thing that really helped me personally and made navigating panels, let's just say possible, like successfully getting through a panel quickly, understanding what I'm looking at beyond just learning the panel because I've worked on it so many times. Like if I walk up to a system that I've never seen before, I don't understand its layout, I don't know where everything is. So let's just say this is a brand new panel to me, but I've got to troubleshoot this thing. The thing that has made that possible successfully, consistently, is learning schematics. And what I mean by schematics is most schematics will give you like your terminal points. So give me 1 second here. Let me grab this one and grab. No, I'd really love a. You know what? Here, yes, this one. We're gonna do this one. Okay, let's talk about this. So this is just one module in a system. This specifically came out of a turbo core. This is a soft start module. But here's some things I want to point out with this. Here's my pointer. So you see that J8, and it's got this pin out here. We can also come over to right here. You see that J1 right there. Then we have a F2 here, this little solid state fuse. So I could go through this board, like this is J9, this is J5, this pin out here is J4. Now, that one you may not be able to read, it's pretty tiny. We have another fuse right here, which is F6, oh, right there. Okay, my point being, these are boards or our schematics. Our schematics will have what your connection point is, and many times it'll even give you the pinout number. So we know that, see, this is my J8. This should be my pin 1 on J8, given my indication here. Now, some of these will actually tell you they'll have a 1 and like a 1, 2, 3, 4, 5, 6. They'll have a 1 and a 6 on either end. That is an immediate indicator as to, okay, the control sequence or the pin sequence starts here. This is pin 1. So when you're reading the schematic, my point is you can get down to learning you can get down to seeing the specific pin when we've got a system that has many pins and many wires coming out of it, and they all say different things. We've got all these pins in this little small strip here. You can kind of see it better right there. All right, there's a whole bunch of little pins in there. We can get down to the individual pin on what we're trying to troubleshoot and what it is that we want to see. I don't want to lose sight of the question here. But that's been the thing that has helped me. I don't have to understand what the whole panel is doing necessarily. I don't have to know everything about this machine. If I know that I'm having, let's just say, a suction pressure transducer problem, and I want to try to troubleshoot that transducer, and I want to verify at the board what that transducer is doing. Well, I can then go to the schematic, and if I understand how to read the legend, which gives you like what each acronym will mean, right? So everything will have a designation. It won't, some schematics will actually just spell it out and say, okay, this is suction transducer circuit 2. Those are cool. But a lot of times it may just say P2. That may be all it says. And you've got to then cross-reference P2 to the legend to then have the legend explain that, okay, P2 is suction transducer for circuit 2. There you go, right? Something like that. And then I can trace those wires. And those wires will be connected to the main board, which the main board may have its own designation like MBB or just MB as an example. So then I can say, okay, I know that just, again, strictly from the schematic, I have my main board, and my main board has the suction pressure transducer tied into it for circuit 2, and it's coming in on a specific set of terminals. So if I look at that where it makes the connection point to the board, it's going to say J5, right? And maybe when I look at J5 has like 12 wires coming out of it, and I've only got 3 going to my transducer. Well, if I look at the schematic, I can see that J5, but it's specifically pin 4, 5, and 6 goes to my transducer. And so let's just say I had a plug that looked like this. This was my J5 plug on my main board. See, right there is pin number 1 on my J5. See, let's just imagine this has J5 right here. So there's pin 1, there's pin 10. That means that all my odd pins are right here. All my even pins are right here. So I go 1, I'm sorry, I said that wrong on this one. I said that completely wrong. Some of them are that way. I should go 1, 2, 3, 4, 5, 6, 7, 8, 9, which we have a 9 indicated right there. I apologize for misspeaking there for a second. It doesn't go 1, 2, it goes 1, 2 like this. So I would then come across and say, okay, this is my J5, and I know that I've got pins 4, 5, 6. So 4, 5, 6 right there. These three are my pins going to my transducer. And then I can troubleshoot further from there. And I take this approach because whenever I sit down and I have conversations with guys around, okay, what are you struggling with? Like, this is kind of where they go. So, okay, well, I got to troubleshoot this component, but I don't really know what to look for, what I'm looking at. I can't sort out all the wires. And you're trying to trace the transducer wire from the transducer back to the board, which is, in some of these panels, it's quite literally impossible to accomplish that. Like, it's just not going to happen. You're not going to trace that from one end to the other successfully. So if you can learn the schematic, just learn the schematic and what the symbols mean, what the legends mean, how to trace and follow them, how to make it through what the schematic is telling you, then you can, for me, it made everything far easier to then go, okay, I can not worry about the rest for now, and I can fixate and focus on this particular sensor because I'm getting this alarm and I need to make sure that this sensor is actually functioning properly. I want to make sure that I'm sending voltage out to it correctly. I want to see what the actual reference signal is because I need to verify, is it my control module, or is it my actual transducer, or is it the harness in between? Like, where is my problem? And being able to find it comes back to, again, the schematic. The schematic is what unlocked all of that for me. Once I learned the symbols, what they mean, what they are supposed to represent, and you can look up a lot of this stuff, but I've also got an entire module where in my online certification course that you can go into, and I talk about the different types of schematics, the different symbols that you'll see, the different layouts of the boards and the modules. Like, I talk through all of this so that you have an understanding of how to translate schematic to the actual panel and what you're seeing when you look at a panel. I break all that down in my certification course at chilleracademy.com. So I can explain it to you there in complete detail, or you can do things like get this electrical book. All right, so this is actually one that I really like. I think they've got a newer edition of it now, but this is a great book, and it has schematic symbols in here. Like, it teaches you a lot. But they've actually got a whole chart somewhere. I don't even remember where, to be honest. Where they're just telling you, hey, this is a table of what schematics can look like. And what I actually did early on is I got a printout of the page in this book. I'd love to find it so I can show you. But I took a printout of the page out of this book so that I could then, I think it's in that diagram section. Where'd that go? Three-phase, reading advanced. Okay, so reading schematics. Like this, honestly, even if you don't listen to me and you just went and read a couple of chapters out of this book around schematics, it's going to do so much to get you up to speed. Like, so here's your legend. This is a ladder style specifically. Here we go. So this diagram, you can't see. Let me show you. My bad. This diagram right here, like, I literally took a copy of this from I went to a printer, scanned it, and had this page, and I carried this around with me. Now, eventually, I took a picture of my smartphone, and I did it that way instead. But like, I carried these symbols around with me, and these symbols are quite accurate across the board. Now, there are more symbols. They get more in depth. This is not everything, but these are at least a set of very basic entry-level symbols to help you get started, and then you can get more advanced with your symbols as you dive into schematics. So That was the big unlock I had personally that allowed me to navigate every panel I walk up to now. Like I am not nervous at all to walk up to a panel, but it's because I know that as long as I have this schematic, I can find my way. I can find my way. So, like if you had one thing you could do, learn schematics and then start letting that navigate you to what you're trying to work on. Learning the sequence of operations is a good start. Yeah, but sequence of operations can also heavily tie into the mechanical side, right? So I'm just devil's advocate on it, right? That's where um, there is an electrical sequence of operations, but they kind of go hand in hand with mechanical. Beginner level BAS class will help you understand chiller control. Yes, that is true. Let's see. I think was it Distech, Honeywell. I think they have some free online beginner level classes and stuff you can do, and yeah, understanding the control logic. But there is a separation here between understanding the logic, which gets back into the sequence, and understanding how to actually work through the panel. There's a couple other critical points to add to that is understanding the difference between continuity or actual resistance. And they're if you use continuity for too much, um, and you're not paying attention to the resistance, like you could be misdiagnosing things. Like resistance to me is what matters, not that it has continuity. That's a whole side trail I'm not going to get into right now. But um, in addition to that, understanding grounded circuits and what a grounded circuit is. And when you're troubleshooting, understand that if you have a grounded circuit and you're trying to find a short, you have to disconnect your grounds in order to fully troubleshoot that panel out. So you could find everything on the schematic just fine, and you're working through the schematic, but then if you don't understand a grounded control circuit versus non-grounded, and if that transformer has an internal ground, then you have to just completely disconnect from it to then find the grounds. Um, so those are just little things we have to take into account that can make a successful or unsuccessful troubleshoot. If you have an ungrounded circuit, but you're testing all your points to ground, you're going to get a bunch of crazy voltages. Versus if you're testing from, say, point to common, then you'll get proper voltage, but then you'll get what we would call a ghost voltage if you test that to ground. So yeah, there's more to tell, but for me, it starts at the schematic. Excuse me. AVWA IGBT exploded. Another company installed a whole new power assembly. Now it's blowing line fuses. Looks like I need to troubleshoot. Oh, wow. Wow, that really sucks. Yeah, I mean, I would start at your, if it trips immediately, I would want to make sure that my phasing is correct, my line reactor is correct, um, and my line reactor is good. Okay, that should have no resistance to ground. That should have no resistance leg to leg, and it should be almost. It should be like when I say no resistance, I mean infinite resistance to ground, infinite resistance leg to leg, and you want to have basically almost 0 ohms or close to it from input to output side of that line reactor. So yeah, that's a pain. It's either that or your SCRs. Those would be the primary things that as soon as it powers up, it's going to blow immediately. Um, it's also possible that like some of those leads, they'll split them off into multiple wires. So it's possible that they may have accidentally crossed a couple of wires coming from the reactor into the SCRs. So be careful, please. Be careful. Yeah, a lot of boards and modules communicate with the main PCB through Modbus. Yeah. Compressor megged good. Not shorted. Check line reactor. Oh, okay. Line reactor wiring good. Got to read further. Unless compressor is locked up, I think I got a problem. Well, if a locked up compressor would not cause the fuses to blow on the power assembly, because then the question I would have would be, do you even get into a charge in the DC bus? So does your DC bus charge? And if you're blowing fuses before you even get to the charge cycle, before that drive ever even outputs to the motor, it's got to charge that bus up. So probably not the motor. If you're popping the line fuses coming in, it's somewhere either from the drive back to line, something in between there is going on. Yeah. And make sure you check those SCRs, man. I'm telling you, those SCRs, they got to be in there and wired in correct, just right. Marker. Can you explain choke and stall one more time, please? Thank you. Yes, 1 second. Let me catch up on this. If I know as a bad line, 2.4 GPM per ton condenser, 3 GPM. I cannot get design data. What do you use for DP to calculate GPM when it's not available? Yeah, baseline, not bad line. I got you. Well, it's 2.4 on the evap and 3 on the condenser. You need slightly higher flow on the condenser than the evaporator. So it's the other way around on that. But if you don't have design, then high level, it depends on the size of the machine. If we're talking about a smaller machine, then typically if I can land between 3 to 6 PSID, especially if it's a two-pass heat exchanger, it'd be two-pass if it was flooded or falling film. Then, which you said it's a YVWA, so you would probably have you've got those use a falling film. For that, I would want to see, being a York, probably around 6 PSID would be kind of my starting point. Now, that is just a out the wall rule of thumb, wild guess. We're just trying to get somewhere in the ballpark. That machine could run anywhere from 6 to 15 PSID, depending on what the specifications was. Like if you don't have the factory specs, you've got very limited ability, and you just kind of have to play with it and find a middle ground and hope that you can get the factory spec. That's really what it comes down to. They really just need to find the factory spec. That's the proper answer. In the meantime, do the best you can. Ultimately, if you can just get the valves full open and get, say, 6 to 10 PSID across the barrel, you're somewhere in the ballpark, and you'll hopefully get it enough to where it will function until you get the proper numbers. Okay, stalling on York centrifugal Millennium. Okay, yeah, let's dive into David's question here on stall and choke. Where'd it go? Right here. All right.
Let's move some stuff out the way. Let me grab some toys here. Hang on. That should sit like that. Is that right? Give me 1 second. Let me get myself situated here. I'll try this. Is our suction. All right. Is that right? That doesn't look right. There it is. Yeah, that's right. That's why it looked weird. Okay. Let's talk about it. Can you explain choke and stall one more time, please? And thank you. All right. Let's talk about stall first. Zoomed out. Okay, so with stall, basically, we get to a condition where the lift becomes higher than we can push it through the impeller. Okay, so by lift is, you think of it as dP or compression ratio. So lift equals dP or compression ratio. I'll say CR, right? Same basic thing, we're just looking at it differently. So by lift, we're saying the pressure difference between evaporator and condenser is X number, 50, whatever. So when we get a high lift, then we get to a point where our ability, so we have the suction side of our impeller here, we have our discharge side here. Our ability to then have that refrigerant come in and then sling out of the impeller gets limited because we can't add enough energy to overcome how much difference we have between the outlet and inlet side of the impeller. Because keep in mind, this is not a positive displacement compressor. This is a aerodynamic, so there's nothing, all this is just open space in between here with some vanes. So just like with a blower motor is the exact same thing, just removing air instead of moving refrigerant. Same exact concepts though. So as this differential between inlet and outlet increase, we get to the point where we can no longer maintain that. And that's when we start to get into a stall. Now, stall and surge go hand in hand. We can hit on stall specifically. And this is also, there's the other question about stalling on a York centrifugal. What I'm explaining is still applicable here. It doesn't matter the manufacturer. We're going to discuss, this is the basics of just how centrifugals function. So we start running high lift. We get to where the refrigerant coming out of the impeller starts to struggle, and we get these little eddy current zones where it just can't fully push through right there because of the built-up differential. All right. What ends up happening is this is referred to as a rotating stall. All right. So as the impeller is spinning, if we're stalling right here in this zone of the volute, so the volute is the housing that wraps around this right here,
could be considered like the type of volute. So this is your discharge coming out of this first stage impeller on this compressor. So this right here is your suction side coming in. This is the backside of your diffuser assembly. So all of this is part of your diffuser. And then it comes out in this little gap right here. Now this is feeding into another impeller, but this is this gap is what would feed into the volute or the discharge pipe that leaves the impeller. So as this is spinning, this section right here is no longer able to move the refrigerant. It literally stalls or it gets stuck in its position. So when it gets stuck like that, you'll hear an imbalance happen inside of the compressor. It gets this really grumbly sound, right? I don't know how else to explain it. It just sounds like a kind of a low end grumble, just like the machine just sitting there kind of rattling. What that is that's imbalance in the impeller. That imbalance is happening because this refrigerant here, as it rotates, the refrigerant is getting stuck. So when everything flows properly, the refrigerant is moving in a free state. It's balanced and everything sounds smooth. But as we begin to stall, then part of the refrigerant in the impeller as it's rotating is not leaving the impeller. And because it's not able to leave the impeller, it becomes a imbalance in the impeller. Anyway, that is what a stall ultimately is. It is hey, this section right here, as this impeller rotates, because we have a high lift and we're struggling to maintain flow through the impeller because of lift, leads to a stall condition, what we would call stall. Now, the extreme of a stall, once we move past just stalling, we can trip over what's referred to as surge, and surge is where the refrigerant reverses flow back through the impeller. And so that's when we exceed the impeller's ability to hold the lift at all, beyond just get into an unstable state. Then we completely overcome its ability to add enough energy to the refrigerant to overcome the condenser pressure, basically. You can think of it like that. And then the refrigerant literally comes in the outlet side and back out the suction and reverses flow back through. This only happens momentarily because then the impeller is going to be able to reestablish, because you're going to have a sudden drop in lift when this happens here at the impeller. When that drop in lift happens, it's going to reestablish flow again, and then it's going to be able to start moving the refrigerant back in the correct direction. And depending on the conditions, it can either then push itself right back into a surge and come back out, or it's going to be able to maintain that and make the corrections that it needs. Now, something that's real important for this is just understanding tip speed. Tip speed has a lot to do with where our stall and surge line are. I completely go through all of this stuff in my online certification course. So if you are enrolled there, I would encourage you spending some more time in those lessons, just trying to absorb this information. But just from a high level review perspective is what we're focused on. So when we talk about stall, like that's what we're referencing, and then we have the surge, and we have our surge line. So getting back to tip speed, there it is. As we're running a slow, if we have a variable speed impeller, as the impeller slows down, our tip speed slows down, which means the amount of lift we can manage reduces. So that's why when centrifugals go into a surge condition, if they're variable speed, they will speed the impeller up. They'll increase speed. What they're doing is they're increasing the tip speed coming out of the impeller, which is giving us the ability to overcome a higher level of lift. Now, to do that, many times we'll close off the guide vanes. So we'll close the guide vanes a bit, and we'll balance the total flow through the compressor via closing vanes and speeding up. And the two, we can maintain the total capacity of the compressor while also overcoming a high lift condition. Um, so yeah, that's just where we get back into um, what tip speed is and why a compressor like this will speed up if it's variable speed when it detects a stall and surge condition, specifically surge. Um, we're trying to overcome the the uh, the lift by increasing the tip speed. All right. Now let's get into choke. Choke is a different. It's basically it's on the other end of the spectrum to all of this. So I'm going to do my best to explain this. Essentially, choke is what happens when we have high lift, or no, we have high flow. So this is high flow with low lift. Choke is something we have to be careful of when we're doing condenser relief, when we're trying to unload the condenser and run a really low condenser water temperature while also having a high load on the evaporator in a lot of process applications or large facilities, data centers, things like that. This is going to be a scenario where you're likely to run into this. We have a low ambient outside. We can get our condenser water down, or we're pulling from a geothermal source of some kind, whether it be a lake or a body of river water or something like that. So we're able to pull from a geothermal source. And get have condenser relief. We're able to get the condenser water down. But if we have a high load, we get to this point where or we basically the impeller becomes unstable in its ability to flow because we're moving more mass CFM through the impeller than what the impeller can maintain due to a low lift, because having lift is important for having the machine function correctly. We do need lift across this impeller to keep the load to keep the loads balanced across it. So when we get really low lift, we have a ton of high flow. We can get to where we can begin to choke the impeller, and it'll create a bunch of instability in the impeller itself. And I'm trying to make sure I'm explaining this correctly. It's something we deal with less often, or at least that's been my experience. Usually we're dealing with a surge scenario, but in a choke situation, yeah, we could end up to where we're just not able to maintain flow through the impeller because there's not enough lift to keep the impeller, uh, call it loaded. Hopefully that makes sense. That's when you're going to run into choke, though. We have really high flow through the impeller, meaning we're moving lots of refrigerant, but we don't have a whole lot of lift. So our evaporator pressure to discharge pressure is really low. You get just the right combination of that, and we will put the impeller in a choke position, which is not good for it. We do not want to do that. Um, yeah. Let's see. Do we have any other? How you doing, Sterling? Good to see you, bud. Just catching up on the comments here. What will cause bearing faults other than lift conditions? Yeah, 1 second. I'm assuming by bearing faults you're referring to like a mag bearing. So let's say a turbo core. That's a dumb question. A few times now I've had high delta T and very high approach at the same time. Yeah, high delta T and high approach is likely going to be a high flow. Your flow is too high, your GPM's too high. And so, well, high delta T does not always mean low flow. Okay, it can mean, but it doesn't always mean. You can have a high delta um, and still have a really high flow. So that would be my concern is, am I having a high DP for that system? All right, let's dive into, let's see. We'll cover quickly the list lift question real quick. All right. And this is on a turbo core. You confirm that. What will cause bearing faults other than lift conditions? So, yes, high lift, which basically high lift, or even low lift for that matter, but more specifically high lift, that's going to push you into, surging potential. And as we push close into surge, that's when we're going to start having instability in the impeller due to that high lift and it trying to not go into a surge, right? So just doing a quick recap on what we're saying when we say high lift or just lift issues causing surging or causing bearing faults. So as we push into a high lift, we get into a stall state. I talked about stall in a previous question where it creates this zone of instability within the impeller because refrigerant can't flow properly. That in an oiled machine just has that low grumble sound to it. In a mag bearing, it can cause enough instability in the bearing that it trigger a fault and it not be an actual bearing issue. So you could have an actual bearing problem where the bearing coil or the sensor or something of that nature is not functioning correctly. It is having a problem, and that's going to cause you bearing faults. High lift with going into stall condition or even surging can also cause bearing faults. It could also be the inverter. All right, so I've got one right here. This is an actual inverter out of a turbo core. We were playing with this earlier in the stream, so you can go back and check that out later if you want. But what will happen is as the inverter begins to get weak and begins to not output correctly, it's not going to maintain a stable field inside of the stator. And as that field becomes unstable, it allows the rotor to have more movement in it. And that movement is going to be sensed as bearing instability, and eventually it's going to become unstable enough that it will cause the bearings to trip out. So if you don't have a lift problem and you're not having an actual bearing issue, where your bearings say they test fine, the sensors test fine, everything checks out perfectly on the bearing side of the system, but we're still having bearing faults and we know we don't have a lift, my inverter is the next thing I'm going to go to check is, okay, is my inverter potentially causing a problem? Now, the inverter could test perfectly good, but still be causing instability. Just because it passes the electrical test you would do with a meter does not mean the inverter is not having a problem. If it's in an early state of failure, which that would result in, say, occasional or at least it started off as occasional bearing faults. It's now escalated. Maybe it's happening more frequently now, but the inverter is still testing like it's in a good condition or safe condition. You could still have a problem regardless. So, because what we're discussing is at some point we get to the conversation of, okay, we're having a bearing fault. If it's a bearing, we're having to replace the compressor, right? If one of our radial bearings especially has failed, that compressor is getting replaced. If we know it's not a lift issue and we know we're not surging, but we don't want to replace the compressor yet, like, it makes sense that, okay, well, it could be the inverter. It may make sense to go ahead, let's do the inverter just in case. Now, obviously, if your bearings test failed whenever you go to check them, then just condemn the bearing. But if the bearings are testing good, typically in my experience, when the bearings test good, they're probably okay. They're probably okay. Then that's when I'm worried about the inverter. Or we could have a demag situation, which is a demagnetized shaft. Now, these are not very common, but they can happen. So the shaft in a turbo core specifically is a permanent magnet shaft. And as that shaft demagnetizes, it will affect the bearing's ability to maintain the orbit of the shaft. So if that, again, just if the shaft itself begins to demagnetize, that's going to result in a bunch of bearing faults. And the thing is, though, if that happens, you're still talking about a compressor. So there's been plenty of times where, hey, the only, out of all your options here, the one that doesn't mean a new compressor is the inverter. And there is not a solid, just this is the only way to verify one way or the other without just trying to replace the inverter, right? So you're going to have scenarios where it just might make the most sense. Let's go ahead, change this inverter out. Let's see how it performs with a known good inverter. And if we're still having bearing issues, then it could be either the shaft, it could be just some residual issue with the bearings themselves, or it could be the calibration. So there's a very specific process to doing a bearing calibration and saving it correctly on these compressors. And it has to be done just right. And if you don't do it just right and there is an issue, then that bearing calibration will completely wreck your ability to safely or to get that compressor to operate. It's just not going to do it. So if having verified the bearing calibration is part of the process of where I'm looking at, okay, are we talking, so lift could be one issue. So specifically when we say lift, we're discussing stall and surge. So stalling and surging could be one issue. We could have a bearing or a sensor issue. We could have an inverter issue, a demag issue, or a bearing calibration issue. Those are kind of the main high-level points that I'm going to be trying to verify in the process. The bearing calibration does not lead to a new compressor. Having stall and surge is external to the compressor. Fix those issues. Why are we stalling? Why are we surging? Okay, and we can address that. But in your case, you specified we're not having that issue. So then that leaves you with calibration or inverter without just recommending the compressor as a whole. It is important to make sure you explain to the customer that, hey, we can either just go with the compressor, which gets you a new inverter, or if you want to try to save this compressor, we can just do the inverter and try to see, are we good? Some customers will go for that. Others don't want to risk it. They just say, forget it. We'll just do a whole new compressor and we'll turn the old one into parts, yada, 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 right? So just be upfront with the customer when you go to explain that. See, liquid in suction will cause bearing faults. Yeah. So if you start well, that's a good point. If you start running a wet suction, whether it be through the economizer or through the suction line itself, both of those, you start having too wet of a suction. Tom is right there. That actually is one that'll cause a bearing fault as well. Which another way to say that in centrifugal terms is carryover. We start having too much carryover. Bearing calibration, see if it's off. You don't need to save it to the EEPROM, validate, compare it to, hopefully, yeah. Yeah, you got to be really, really careful with those bearing calibrations. And I've had people go in and do a bearing cal on like maintenances and stuff and just completely screw it up. And take a perfectly good compressor and have it just not function without getting the calibration correct. Shows up bad. Bearing calibration shows up bad. Smaller than normal, sometimes out of place. Only the front bearing. Everything else tests good electrically. How fast does it show up? Immediately or sometime after startup? Yeah, that's a good next question, Jason. How quickly does the fault appear? Yeah, let's give him a second to respond to that. That is a good question that could help kind of navigate this. Yeah, sometimes out of place. I don't get how you mess up the calibration on a turbo core. Yeah, if you go to do a calibration check and then you save it and it was a bad calibration, as in like there's all kinds of little things that can influence, and this is just how I've been trained on this process. You're supposed to completely disconnect everything else like from the IO module, unplug everything else from the module, don't have anything influencing this compressor. We want to put it through a calibration check. And then like you don't want to save the calibration from the factory cal unless you absolutely have to. But not everybody does that and they end up saving it. And then that calibration is a less good calibration and it just ends up throwing the whole thing out of whack. It's very intermittent. So it sounds like being intermittent sounds like you're able to come online, get past startup, get an operation, and then you end up going into a bearing fault. Oh. Yeah, I mean, I would come back to what we've been discussing. If you're I wouldn't want to jump to updating the bearing calibration yet. Shows up bad, smaller than normal, sometimes out of place. Yeah, so we're having issues getting the bearing tests good electrically. The bearing tests good electrically, but the calibration is showing the front bearing is having an issue. Yeah, I mean, at that point, the calibration is not going to be influenced by the inverter. So by the calibration showing an issue, like going through the calibration process, we can rule the inverter out as a potential. So at that point, we've either at that point, the conversation becomes, okay, is it is it that front radial, or is it the is it that shaft demagging? I'm really hesitant to suggest a demag because they're really not common. It can and will happen, but it's not that common. And if it is, if you are seeing it, it's typically because, or at least from my understanding, overheating in the compressor and the cooling circuit not functioning properly and maintaining the stator temp. So either the cooling circuit having an issue not maintaining stator temp, or the inverter causing an issue due to it getting weak, which also generates a lot of extra heat. So point is that rotor is getting hotter than it should be, and if it's able to run like that for a long enough period of time, it will eventually cause the shaft to begin to demagnetize. So that's my understanding as to what leads to a demag typically. Actions, thought it might be cable, replace the cable, but still issues. Always front radial fault. Pull the log, see. I mean, if it's able to start up and run long enough that you can walk away from it and you're not seeing it happen, like seeing it happen live in front of you, then you probably are looking at a you probably are looking at having some kind of lift concern, either lift or you're running a wet suction, something like that, after you leave. So these Tom and Jason have really solid points of like we if it's not tripping this with it in front of you and you're able to verify that, hey, lift or our refrigerant level in the evaporator, because you can monitor your suction superheat on this. And if that suction superheat is still high and your discharge superheat is high, so that's the things we want to be paying attention to. You've still got adequate discharge and suction superheat. If you're seeing those drop, so you're seeing low superheats, you're running a wet suction, period. Whether it be from the economizer side or from the evaporator side, saying you have a economizer installed with this compressor. So what are your superheats doing beyond just, so I'm not arguing with you on lift, right? You say we don't have lift issues. I got it. What about superheat? What are your superheats doing when the compressor is online or when the trip happens? So if you look back at the logs, like what are your superheats showing in the logs? Because if it's the evaporator side, you'll see it on the suction side. Will be really low superheat. And if it's the economizer side, then you're going to see it on the discharge only. You won't see it on the suction because the economizer bypasses the suction. It comes in on an intermediate point. Having sudden load changes. That's a good point. That's fair. That's a fair question. Yeah, once we wrap up with this, guys, we'll wrap up the stream. But let's stick with this and kind of talk through this some more. Let's see if we can collaborate and come to a solution here. Because it really is kind of painful. You get into these bearing faults, like that is the number one complaint with turbo cores is bearing fault, bearing fault, bearing fault. And reality is they're not that easy to troubleshoot, especially if you just haven't had to do it for years on end. So yeah, I appreciate everybody's taking the time to give some input here, and let's see if we can help Matthew kind of talk through this. Wanted to mention also on the YVWA power assembly, it's only blowing fuses on circuit 2. Circuit 1 runs fine. Okay. Probably an old return date. uh, no sudden load changes, only happens on one compressor. Wouldn't lift issue show on both. Not necessarily. To your point, more. I mean, you would expect to see some kind of issue on both of them, but not necessarily. Not necessarily. And it could be even if it's running a high evaporator level, you may not see it reflect the same on both compressors. Now they shouldn't be like horribly far apart from each other, but they may be just different enough to where one is seeing it where the other one's not. Because all that plays into like where's the suction line in orientation to the evaporator. You know, this one's pulling from this point on the evaporator, this other one's pulling from this other point. How that pulls back up into the suction, all it gets affected at that process. So yeah, I'd really like to know what your superheats look like at the point of a trip. So let's see. If it was truly a DMAG, I mean, that's going to be intermittent too. Well, if he has a damaged impeller, that's going to come back to a wet suction issue anyway. So we're still discussing like having carryover issues at that point. The compressor being level, how level it is, to my knowledge, does not affect the turbo core so much. So I don't know that it's going to be how level is it. At least if that is a thing, I've never heard or ran into that personally. So that would be news to me. Yeah, not to put you on the spot, Matthew. We're not trying to harp on you or anything. And we get you may not be able to, you may not have quick, easy access to the data we're asking for. It's just if possible, it would be. We're just trying to help, right? You obviously you may be in the middle of something that getting the data may not be so easy. You can always follow up with me separate via email if you want to. We can always come back to it and revisit it in next week's stream or something. So we've got other options here beyond just today. If you wanted to share that data log, that would be helpful. And I could go in and kind of see for myself just kind of how it's behaving. And like I said, we can make a whole group discussion out of it if we wanted to, and just seeing the behavior of the system via the log. So yep. Okay. I'm gonna wrap it up here, guys. Hands-on classes, schedules available at chilleracademy.com. Go check it out. We've got 4 classes coming up this fall, 2 in Fredericksburg, 2 in Houston. They are beginning to book. We've got quite a few people grabbing seats. So I would suggest if you want to jump in on that, grab it now. And with that, also, I've got my online certification course. I got a lot of stuff we went over and discussed and talked about today, like in terms of definitions and just everything I've discussed was just very high level, just trying to get some general understanding out there. I go much deeper into all of these things in my online certification course. So if you genuinely want a complete picture on how all this stuff works, what it looks like, everything else, that's the place for that specifically. And my hands-on class is focused on these hands-on procedures. We don't get to spend a ton of time on entry-level basics on how these things work because we're so focused on various processes, procedures, troubleshooting. So that is one of the things. Like we don't get to cover a lot of that information. So if you are looking to go to a hands-on class, I highly recommend spending time in the CERT course first. It's not required, but it is recommended so that you can come in kind of having those basics already out of the way for yourself and you can truly focus on, okay, this is how to do these things specifically. With that, I really appreciate everybody's time. Hope you enjoy this, our first stream here at the new setup and just enjoying the new facility here. It's been awesome. I really appreciate the support and I look forward to just working with everybody over time. It's great seeing you all. With that, MTT, make the time for your family, for your spouse, for your kids. They really need you. We're in the throes of busy season. This ain't easy. I'll see y'all later.